David is Canadian in origin. He received his BSc in physics from Waterloo, and then did his PhD at Harvard in 1978 under the supervision of Professor Tinkenham. He spent 17 years until 1995 in Exxon Research and Engineering Corporation. And after a few years in UPenn, he returned to Harvard, where he is now the Melincott Professor of Physics and Applied Physics, Director of the Harvard Material Research Science and Engineering Center, and a professor in the Department of System Biology. Dave is by far the most productive soft matter physicist, with hundreds of peer-reviewed papers and over 65 patents. His papers have over 65,000 citations. He instructed an incredible number of roughly 200 PhD students and postdocs. Most of them hold prominent positions in academia and in industry. Dave is an elected member of the National Academy of Sciences, member of the American Academy of Arts and Sciences, of National Academy of Engineering, and is a fellow of the American Physical Society. Dave and his group study the physics of soft condensed matter. The group studies both synthetic and biological materials, with interest ranging from fundamental physics to technological applications. Weitz is also the co-creator of the popular Science and Cooking course at Harvard, and some of his experiments were conducted in space. Today, Dave will tell us about new routes to amorphous structures. Dave.
So thank you very much. Let's see, I don't think I can compete with the beauty of the music we just heard, nor with the elegance of the symmetries that were discussed in the first talk. Instead, I'm going to do exactly the opposite and tell you something about the lack of symmetry, at least the lack of crystalline symmetry. Tell you something somewhat more experimental, and try and describe two different things that we've done recently that describe how you go from the crystalline state to the amorphous state. The work is that of several of the people in my group, primarily that of Joris Sprakel, who is now a professor in Holland, and Esther Amstead, who's a professor in Switzerland. And all of it's done with my colleagues Franz Papen and Michael Brenner. I'm going to try and tell you two different stories. One is something about a very fundamental question that's surprising. It actually dates back to Born. It's something that, at least to me, was less known about the work that he did. He described something about melting, how crystals might melt. And I'd like to tell you some insights that we've been able to gain about that kind of system. The second thing is a much more practical thing about how to make materials in amorphous state in a very, very simple, pragmatic, and useful way. Something that was a big surprise to us, the fact that they became amorphous and has actually a lot of potential applications. So first, let me talk about the simple idea of the solid to fluid transition, or how crystals melt. Actually, this is very well known. They melt on the interfaces. They melt because of heterogeneous locations of some kind of surface. For example, there was a beautiful study by Arjun Yode, who's at the University of Pennsylvania, using colloidal particles as mimics for crystalline materials. And he showed that melting always occurred along lines of defects where there was an additional volume. They occurred always at the interface. And that's exactly what you would expect. If you have an ordered, symmetric state, a crystalline state, and you ask how does it melt, it always melts at the interface. It melts at the surface melts away. But what happens if you have a system with no interfaces whatsoever? Well, actually, the person who considered this was Born in 1938. He asked the questions, what happens if you don't have an interface, if you can't allow the system, if you don't allow the system to melt at the interface? In that case, he predicted there should be essentially an elastic catastrophe. That is, you should get closer and closer and closer to melting, and eventually the system just falls apart. It undergoes some catastrophe. It suddenly turns from a crystalline material to an amorphous material, to a fluid. Essentially, the elastic modulus, the thing that defines the existence of a crystal, goes to zero, and the crystal melts. But how does this actually occur? Can you actually see this? Well, to address this issue, we turn to a system that actually was studied many years ago in the 1980s. Actually, was studied when I worked at Exxon by a group of physicists at Exxon using colloidal particles. And they made what they called a Wigner lattice. A Wigner lattice is a system made completely of repulsive particles. And you might ask, well, how can repulsive particles actually form a crystalline solid? The answer is that if you confine them, you put an osmotic pressure, you put a pressure on them to hold them together. If their separation, the average separation of the particles, is less than the distance that the repulsive interaction occurs over, they will form a crystal lattice. And these experiments were done with 91 nanometer polystyrene spheres in water. You can't really see through them, so they used X-ray scattering. The length scales are relatively short. They're sub-micron length scales. And so X-ray scattering was the only way that they could resolve the behavior. And they saw a classic. This doesn't really, the quality of this, the projection is not really good enough to see it, but they saw a standard kind of behavior where as the system melted, it went from an FCC lattice, face-center cubic lattice, at high concentrations to a BCC lattice near where it melts. And in fact, many, many materials undergo this transition. They undergo an FCC to BCC transition as they approach melting, basically because the BCC lattice has the symmetry that's closest to that of a fluid. It has the loosest symmetry. So we set out to try and mimic this behavior, but we didn't want to use the aqueous system, which has a very high dielectric constant and therefore very short length scales, using charge as the means for repulsion. So instead we used a non-aqueous system, and this is a system where, because it's in an oil, the dielectric constant is much lower, the length scales become much larger, and you can use confocal microscopy to actually view the particles. And here are the way the particles look. In this case, they're not charged, and so you can see they are randomly situated. They can occur at any positions relative to their neighbors, except, of course, they can't overlap. However, we've developed methods, even though this is an oil, we've developed methods to charge the particles. And normally you don't think of putting charge in an oil. However, if you can somehow carry the charge in the oil away from the particles, you can allow them to be charged. And the way you do this is to put surfactants in the oil that create small, very, very small regions of high dielectric constant in which the charge can be located and which solubilizes the charge. And if you do that, you get a system that looks like this. Now you can see that the particles really have a characteristic spacing between them. They're charged. They feel the repulsion of each of the particles, so they can never approach one another very closely. And instead, there's a certain ordering that you can see due to the fact that they're charged. Now, this system we can adjust both the charge and the concentration. We can adjust the charge essentially by changing the amount of surfactant in the solution, changing the amount of charge that can be solubilized in the oil. And we can adjust the concentration just by changing the number of particles in the suspension. Now, changing the concentration has the effect of changing the temperature. As you increase the concentration, that's like lowering the temperature because you're pushing things together against the repulsive interaction. So we can change the temperature and watch the system undergo a solid to a fluid transition, not by changing the temperature, but rather by changing the concentration. So if you look at a sample that's at high concentration, this is like at a low temperature, and this is clearly a solid. This is in fact a face-centered cubic FCC lattice. If you look carefully, you see that this is actually a movie, and the particles are undergoing fluctuations. There are actually some phonons that you can see in the system. The particles are thermalized, they fluctuate, but they remain spatially in the same location. They're a crystal lattice. You can lower the temperature by going to a lower concentration, and this is what a somewhat lower concentration, so a higher temperature looks like. And now you can see that the fluctuations become much larger in magnitude, and the separation between the particles, of course, gets larger as the temperature the effective temperature gets lower. And you can go even lower in temperature, or even even higher in temperature and lower in concentration. And now you see the particles are well separated. They're fluctuating an enormous amount. You can see some of them seem to go out of the plane of view that you're observing. But although they fluctuate, they remain in their symmetric positions in their crystal lattice. They can fluctuate a very, very large amount. Nevertheless, they're still crystalline. In fact, in this case, the lattices change from FCC to BCC. And you can look at the phase diagram. These are just snapshots of the images. Of course, the phase diagram now, in this case, is just the concentration. At low concentrations, that's at high temperatures, it's a fluid. At high concentration or low temperatures is FCC. It transitions to BCC. And there is, in fact, a small region of coexistence between the BCC and the liquid. And you can see each of these in real space in these images. You can also do the more traditional thing, that is do scattering. You just take the images and Fourier transform them to find the scattering. And you can see the FCC and BCC scattering. In the coexistence, you can do from both the liquid and the crystal region, and you can see part of it's BCC, the other part is fluid. Of course, in the fluid region, you no longer see the peaks in the Fourier transform. You no longer see the scattering of a crystal, but rather it's a liquid. And you can average the G of R's, and you can see exactly the same kind of behavior. So now you really have the ability not only to study the melting, but also to look at the particles themselves, understand the nature of what's happening by looking at this model system, by looking at these colloidal particles, where the motion of the particles themselves mimics the behavior, and the particles exhibit the phase behavior that allows you to look at this melting in the absence of any phase boundaries. So again, the system is held in place by the walls of the sample container. So you can look across the whole system and you see no defects. It's a perfect lattice across the whole system. So this is really the infinite system and allows you to look at this question of what happens in melting when you don't have an interface to address this issue that Bourne was discussing. So the first thing that you can do is just measure the fluctuations of the particles, measuring the mean square displacement of each of the particles. And if you ensemble average, if you look at in the fluid, you see something that the mean square displacement increases linearly with time. It's essentially diffusive motion. And there's a transition where the mean square displacement no longer increases with time, but rather is fixed in time. It doesn't change with time, and that's consistent with the fluctuations that we saw. Nevertheless, there are clearly fluctuations. They just don't change in time. And that's what we saw. The particles remain fixed in position, but they fluctuate a lot in time. Now, what's particularly interesting in this system is you can look at the amplitude of these fluctuations. These are systems that are getting lower and lower in concentration, and therefore approaching the melting, and you can see the fluctuations are increasing. And if you just plot the value of those fluctuations, this is what's called the Lindemann criterion. That's the amplitude of the fluctuations compared to the lattice constant, the average, ensemble average fluctuations. And it's shown here from as you decrease the volume fraction, that is, as you approach the melting, it increases and ultimately melts. But if you look at the values, if you can read these, this is 0.2, 0.25, what's surprising about this is that if you look in the literature, the Lindemann criteria, the standard rule of thumb is that when the Lindemann criterion is 0.1, the system melts. So here we see much, much larger fluctuations than most solid materials because you're getting much, much closer to the melting point while it's still remaining crystalline. And so the Lindemann parameter becomes much, much larger. And you can calculate or you can say, well, okay, look, the average Lindemann criterion at melting is something like 0.25. But you can look at the individual particles and ask, what are their Lindemann parameters? You just measure the fluctuation for some period of time of each of the particles, and you find that some of the particles have Lindemann parameters that are much larger than that of the melting value. They have these enormous fluctuations. And remember, they have these enormous fluctuations, but they still retain their positions on the crystalline lattice. And you can plot the number of particles that exceed the average value that would cause them to melt. And these are essentially particles that are fluctuating this huge amount, and therefore you could call them superheated particles. They're much hotter, they're much larger fluctuation than otherwise. And you see that the number of particles, or the fraction of particles, as it approaches melting, gets very, very large, and ultimately, of course, the system melts. So even though you can define an ensemble average value, there are many, many particles that have a much larger value. In fact, the same thing is observed in simulations using for metallic copper, using a full quantum mechanical description of metallic copper. You see that as it approaches the melting point, the number of very, very hot particles becomes much larger. And this is something that you can't see with scattering experiments because you can't really resolve the atomic fluctuations. You can only do the simulations. So you can look at these superheated particles, and you look, first of all, you see that the number increases exponentially as you approach the melting. So if you plot the difference, the volume fraction difference, you see an exponential increase of the number of particles approaching melting. This is exactly the same thing that we're seeing in these simulations. So now we're in a position to really ask much more detailed information. This is clearly a system that has no interfaces. Nevertheless, it undergoes a transition between a solid and a fluid. It undergoes a melting transition, but it undergoes a melting transition in a very unique and unusual way. So we can ask the nature of the Bourne transition. So first of all, because we can look at each of the particles, we can visualize the individual particles. And in particular, we can ask, if we see these superheated particles, are there spatial correlations between the particles? Does one particle, the fact that it's superheated, does that drive its neighbors? Do you see something? Is there some insight we can gain by looking at the spatial correlations between the hot particles? So we can do this just looking spatially in the system. This is now just looking at a confocal three-dimensional image. We're imaging each and every particle. We're measuring the local fluctuations of the particles. And if their fluctuations are below, are less than the melting value, so they're not superheated, we draw them as small spheres so you can look through them. The large spheres represent the superheated particles. And this is looking at a system that's well away from the melting, that's a very solid-like system. Nevertheless, you can see some superheated particles. And what's interesting is that there's relatively strong spatial correlation. In fact, when I draw these particles in red, these are particles that are joined as nearest neighbors. They're all superheated, and you can see that they form this relatively large cluster in the midst of a random system where there's only a few small clusters, but only a much fewer number of superheated particles. However, as you further heat the system, that is, lower its volume fraction, then you find that these superheated particles exhibit this very strong spatial correlation. And these are the red are the largest clusters, the green are the next largest, the blue are the smaller clusters. And you can start seeing this distribution of clusters, but there's a very strong spatial correlation. And as you come much closer to melting, you see that this spatial correlation persists and in fact grows. The particles don't exhibit a random distribution, but rather exhibit some very strongly correlated distribution, some very strong extended connections between the superheated regions. So I like to think of them as I have this system where the particles are more or less stationary, but you have these extended regions, extended clusters of very, very hot particles, particles that are undergoing much larger fluctuations. Of course, if you look at the system when it's completely melted, then everything has a much larger fluctuation, and you don't see anything in particular. So the hot particles are strongly correlated in space, and we can start looking at the nature of this correlation. The first thing that we can do is measure the structure of these correlated regions. And not surprisingly, this structure is fractal. So if you plot the number of particles, that's the mass of these clusters, the number of particles in each of these clusters as a function of the radius of gyration. Just calculate the radius of gyration as you would normally calculate the radius of gyration of a polymer. You see that there's a very strong correlation, and it's a power law correlation. The fractal dimension is about 1.7. That means that you can you can fill space with these highly overheated particles, superheated particles, without using all the particles. You can nevertheless fill space because these are fractal in nature. They extend much larger than their mass would demand or would allow. And you can look at the distribution of these particles, and you see that there's a power law distribution. The power law is a power law of 2, and there's an exponential cutoff. Actually, if you look at a variety of theories for understanding power law distributions, for example, the Smolchowski theory, whenever you have a power law of 2 for the mass distribution of a power law of 2, what that means is that you can extend through all space. You can gel. You can form a connected network that extends through all space once you have a mass power law of 2. And this is, in fact, then one sort of physical way of thinking about what's happening. You have these superheated regions. These superheated regions grow as you get closer and closer to the melting. They grow and eventually fill all of space with these superheated regions. This might be one physical way of thinking about the nature of the melting. However, what's quite interesting is that if you plot the mass as a function of this normalized distance from the melting, you see a power law distribution. So these are the average mass and the mass of the largest cluster. You see that as they approach, they exhibit this power law distribution. I'm plotting on a log-log plot the mass as a function of the separation, the normalized separation from a melting. And you see a power law distribution. Well, what does a power law distribution remind you of? It reminds you of a critical behavior. It reminds you of some critical transition. But remember, this is melting. Melting in 3 dimensions is normally not thought to be critical. It should be a first order. Nevertheless, you see this critical-like behavior. In fact, you see it in other ways as well. If you look at the volume fraction of the clusters, and again plot that as a distance from the melting, you also see a power law distribution. And If you plot the elastic constant, this is in fact exactly what was predicted by Born, and we measure this by measuring the C4 flow, one of the elastic constants, which you can measure optically just by measuring essentially the shear of neighboring particles. You again see this scaling-like behavior. In fact, this was inherent in the predictions of Born, although he didn't recognize it himself. If you replot his data or his calculation, you see the same things. So look what I'm showing you. You have a scaling behavior, that is a critical-like behavior of the cluster size distribution, of the cluster volume fraction, and of the elasticity. So what this says is that even though you are not near melting, you can be away from melting, you can be at any point, and you know how close you are to melting. You know how you're approaching melting. This is exactly the type of behavior that you would get if you had a second order or critical-like behavior. But this is 3D melting. And this is not a critical behavior because there's clearly a coexistence between a liquid and a solid phase. And we look very carefully and ask the question, well, are we really seeing a coexistence? Could it be that there was some time evolution that we didn't quite reach equilibrium, but we convinced ourselves that in fact there is a strong coexistence. So we see this dichotomy. We see something that is clearly a first order behavior, clearly has a coexistence between a liquid and a solid, but nevertheless has this critical-like behavior. So it's only weakly first order. So how can we understand that? Well, we tried to ask, is there something different about the particles? So we looked, for example, at the Voronoi volume. That is the volume around each of the particles, whether they were superheated or not. And you can see the blue and the red are the difference, are the Voronoi, are the distribution of Voronoi volumes. And there's really no distinction. You can't really see any difference. So you can't really tell the behavior. So instead what we had to do was actually look at the nature of the fluctuations. And remember I showed you that the fluctuations can be enormous. They can be very, very large. And so normally when you treat systems like this, when you treat the elasticity, you treat things only in a linear approximation. The linear approximation assumes that the fluctuations, the motion of the particles are relatively small or that they're affine. But it turns out that because the motion of the particles are so large, they're displaced from their equilibrium positions by such a large amount that any kind of a fine approximation, any kind of linear approximation is no longer sufficient. And you have to extend the theory of elasticity into the non-affine, the non-linear regime. And basically what you have to do is you displace one of the particles and you have to do a force balance. You ask what the balance of forces, and it disrupts the balance of forces, so the particles have to move to account for that. That also explains why the neighboring particles, why these hot regions are so strongly correlated in space. And once you do this, you can look at the non-affine motion of the particles, and you see that it peaks around the melting transition. This is exactly what you would expect. So what you have to do is recalculate the elastic modulus. You can no longer use the linear calculation for the elastic modulus. And when you do that, when you recalculate the elastic modulus, this is the Born calculation as a function of volume fraction. When you include the recalculated non-affine region, you see exactly what you measure. You see this melting behavior. So what this says is that the nature of the Born transition, the nature of the melting in the absence of interfaces, the sample can become itself very superheated because there's no way for it to melt. There's no way to nucleate the melting. Instead, the sample is perfectly ordered, it remains ordered, and it gets larger and larger fluctuations, and the degree of first order transition becomes weaker and weaker. That's why it begins to look like a second order transition. But what's really happening is that you're driving it much, much harder, you're making it more and more superheated, and it's this non-affine, non-linear effect that's causing the melting. So this is sort of interesting because if you look at the second order nature for melting, 1D melting is always second order. You can't have first order melting. 2D melting, well, the Nobel Prize, in fact, was given in part for things like this. Some of the people who won the Nobel Prize this year contributed to the idea that in 2 dimensions, melting is actually a second order phase transition because it undergoes this hexatic transition. And here it shows that in 3D melting, you can have something that is close to a second order phase transition, although it's not strictly a second order phase transition. And so it's the non-affine shear modulus, as I said, that's really provides the weakened regions, and it's this that's driving the melting. And this is what's leading to the catastrophic failure of the elastic transition that was first predicted by Born many years ago. And it's sort of a generalization of Born melting. If you want, it's something that gives you more intuition about the nature of Born melting. Okay, so that's my story about trying to understand how you can take a solid and make it into an amorphous, into a liquid. Now I'd like to ask a more practical question, and that is, how can I very generally make amorphous materials? And this turns out to be actually fundamentally important, both from an interesting scientific point of view. It's actually a very practical very practical importance, because many materials are crystalline, and crystalline materials are completely, or can be completely or very very poorly soluble in a fluid. For example, if you have a hydrophobic material that's crystalline, it's not soluble in water. If you have a drug that's hydrophobic, you can't use it. It's not useful because it doesn't dissolve in water. It's not available for the body. If, however, you can make something amorphous, the solubility of amorphous materials can be much, much larger. So I'd like to discuss a very, very simple way to take crystalline materials and make them amorphous. And so how do you normally do this? Well, you know you can make amorphous materials like amorphous metals. You can make them by very, very rapidly cooling. But to rapidly cool something and make it amorphous, you have to avoid the crystallization region. And that's actually fairly difficult. Nevertheless, people are becoming very adept at splat cooling, rapid cooling of metals to make them amorphous. You can do vapor deposition, same thing. You're depositing things so rapidly that you can make them amorphous. A much more common way is to spray dry materials. And you might think that you can very easily make things amorphous by basically spray drying is nothing more than taking a material, making it soluble in some solvent, making a small drop of the solvent and blowing it through hot air to evaporate the solvent, and the precipitate becomes a solid particle. It's a very standard, very, very widely used technology for making materials, and you would think that it would be a very good way of making an amorphous material, basically because as you evaporate things, you might be able to make the material become amorphous. However, unfortunately, crystallization is always faster than evaporation, or almost always faster than evaporation. So this always makes crystalline materials. So to overcome this, what's often used is you add some excipient, you add something that prevents crystallization. And this is a common way of making amorphous materials. Basically, you spray dry them and make them into something that's amorphous, but you always have to add something to prevent crystallization. So you can buy spray dryers. And if you want to make very small particles, which again is a very useful goal, how can you make really, really small nanoparticles? Well, you buy a nanobuchi. Buchi is a Swiss manufacturer of spray dryers. Actually, if you look at the particles, this is a 2-micron scale, so even though they say they're making nanoparticles, there are many thousands of nanometers, or really microns in size. So we took a slightly different approach, or basically Esther Amstead took a slightly different approach when she spent some time as a postdoc in the lab. And she tried to make a spray dryer using a technology that we use for a lot of other things, and that's using microfluidics. So all she did was she made some channels, and she tried to make drops of one fluid, but not in a second fluid the way we normally do, but rather in a gas. So here is, you can see that actually this is a movie that's playing. There's a fluid coming here. We're actually mixing two fluids, and we're blowing air through here, trying to make particles, and we just cut it off here to make a spray dryer. And if you look at that, you see that it makes small particles. These are 1 micron particles, but these actually are particles as well. So it's making some interesting particles. It's making some very small particles and also some very large particles. So Esther asked a very simple question. Here you can see that what's happening is when you're forming the fluid in the air, you're making a jet of a fluid. She asked, can we make drops in the air? Can we make a drop of a fluid in air? Imagine like a faucet going drop, 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 drop. Can we do that using air to create that? And so what she first did is she tried to increase the number of channels of air, but if she did that, you see that it's starting to form drops, but it's still forming a jet. So she asked the question, do we understand something about the nature of the transition between dripping and jetting? And the answer is yes, we understand that quite well. In order to have a dripping transition, that is, in order to form a drop, you need to have a stationary transition. That is, you need to have a drop form without the interface moving downward. So you want to have the drop form without having a velocity. The problem is, of course, that you need to blow the air in to create the velocity to break the particles from the incoming fluid. So how can you do this? This is sort of a dichotomy. But she understood something very simple. So here's the geometry that I showed you. The fluid is coming here, the air is coming here, and you think you need to have a very large velocity of the air. So there's no way you can have a stationary interface. There's no way you can have a velocity equal 0. But Esther said, well, look, there's a very, very simple modification in the geometry that you can do, and that is, you can reduce the flow of the air just by changing its direction. So rather than bringing the air in the same direction, in a co-flow direction, she brought it in the opposite direction. Now the point is that the air has to go this way, but it's coming this way. So there has to be some point of stagnation. There has to be a point where the velocity in this direction goes to 0 because it's changing direction. In both cases, it's changing direction. Now you have a very, very simple way to create a stagnation point, to create a point where the velocity of the air is 0. Nevertheless, you're still blowing the air and you're still forcing the drops to form. And when she did this, she formed drops right away. See, this is now, these are all channels of air. This is a channel of air, but she's bringing it in the opposite direction. And now you're getting drops that form right away. So now you can start looking at the drops. You can see this is taken, these images are taken with a high-speed camera. You can actually watch the drops as they're formed. So you can do things like measure the velocity of the drops as they go down each channel. You can calculate this. All the pressure in all the inlet channels were the same. You can use essentially Kirchhoff's law to calculate the flow of the air through all the channels. You know the velocity of the air. You actually can measure the velocity. You can just seed it with small particles and measure it, and you can measure the velocity of the drop. And this is a plot of the velocity of the drop. Actually, if you measure the velocity of the air, you see that the air is always something like a factor of 10 larger than the drop. So what does that mean? That means that as the drop is going down, the air is rushing by. It's moving a factor of 10 faster than the drop. But look, the drop has essentially the same diameter as the channel. You can measure the difference, in fact, just by taking an image and looking at the videos. You can say, well, maybe there's a gap between the channel and the drop of about a micron. So you're forcing the air around the particle through a gap of a micron, and the air is moving a factor of 10 on average, a factor of 10 faster than the particle. So of course you're accelerating the particle, but you're also blowing the air by very, very rapidly. So if you just calculate what the velocity of the air, it's something like 60 kilometers a second. It has to be that fast in order for the air to go by the drop. That's like Mach 180. It's really going very, very rapidly. So what does that mean? The air is blowing by very, very rapidly. I don't really know how to deal with the fluid mechanics, the Navier-Stokes equations under this condition, but I can be very naive and I can say, well, look, let me just calculate the viscous forces and let me calculate the surface tension forces, the capillary forces, and let me just equate the viscous forces and the capillary forces, because if I do that, I get a size. And the size that I get is about 300 nanometers. And then I can ask, if I put some particle or some solute inside the solvent, if I put something that will precipitate inside the solvent, I know the concentration. So I'm going to show you cases where I put a known concentration. What's the size of the particles that I'm going to get? It's something like 30 nanometers. And if you look, this is just looking at the outlet, if you look, that's exactly what you get. You get tiny, tiny particles. You get nanoparticles, and now these are very, very uniform. So the way you have to understand these is that you're tearing apart this drop. You're tearing it into much smaller drops. We call this a nebulizer. We nebulize the drop. We break it into tiny drops, and the measure of the size of the drop is just given by the particles that you produce. So here's a very, very simple way of producing nanoparticles by nebulizing the fluid, by first breaking it into a big drop and then breaking the big drop into much smaller drops. And you can do this. You can vary the pressure that you use to feed the air, and you see that as the pressure goes down, the particles go up, and if you just, the size of the particles go up, that means the drops that you're forming, the secondary drops that you're forming goes up, and you can plot this, or you can say, well, okay, I'm changing the shear, you can calculate the change in shear, therefore the change in the size of the drops, and you get exactly what you would expect. It exactly behaves the way you would expect. And you can use this, we've done this for a lot of different materials. These are barium sulfate, calcium carbonate. All of these things are done with water. There are many other permutations. For example, in this case, what I showed you, you form drops. Sometimes the fluid wets the solid, wets the channel. Then you get slightly different behavior. I won't go through the details of this. Essentially, what you do is you get a very thin film that coats the side, and then it breaks, and it's like, imagine if you've ever seen these pictures where something falls on the surface of water, and you get something, a plume that comes up, and you get a ring, and then it breaks into drops. The same kind of phenomenon is happening here. You have a very thin ring, and it's breaking into drops. The thickness of the ring tells you the size of the drops. And again, you can go through the same behavior. You see exactly the same type of behavior. You form nanoparticles. Their size depends on the velocity of the air. I won't go through the details. It works exactly the same way. And again, here's another way you can make, with all different materials, anything that you put in that precipitates from the solvent, you create these nanoparticles. But here's the really interesting thing. If you look at the nanoparticles, you see that, in fact, the larger particles, you can see crystal lattice. The smaller particles, you no longer see any remnants of crystals. All the materials that I showed you are materials that form crystals. They're all organic or inorganic materials that want to crystallize. But if you go to small enough particles, you completely lose any semblance of crystallinity. You can see this if you do DSC, differential scanning calorimetry. This is a peak. This is a melting peak due to the existence of a crystal. You lose that. If you do scattering, These are the spray-dried particles. This is a reference. This is the spray-dried particles. If you make them small enough, you completely lose crystallinity. So basically, if they're about 20 nanometers, 15 nanometers or smaller, they're completely non-crystalline. They're amorphous. So how do we understand that? Well, remember I said that if you do this evaporation, you would expect still crystallinity to occur. But if you make the particles, if you make the drops very, very small, then they're going to evaporate much, much faster. Nevertheless, crystallinity should still occur. So what you have to do is you have to worry also about the cooling effect. You're evaporatively cooling. Well, you can calculate that. Because the flow is so rapid, you can calculate what the boundary layer is, and you can use simple kinetic theory to calculate the rate of evaporation. So what's happening? Well, always when you have a system that wants to crystallize, as you change the concentration, it's going to undergo spinodal decomposition. So if you increase the concentration to the point where it crystallizes, there's going to phase separate. Before it crystallizes, it's going to phase separate due to spinodal decomposition. If you're in this point, it's going to phase separate here to something where it's highly concentrated, and here where it's something where it's very low concentration. The high concentration is very strongly cooled because of evaporative cooling. It's so strongly cooled that the mobility of the particle, of the atom, of the molecules, is very low. So you're forming this supercooled network, or this cooled network, this glass-like network. You're basically below the glass transition, and you form a connected network that's a spinodal network that things are going to crystallize, but it's going to take a long time because it's so cold. In the low concentration region, the concentration is so low that it won't crystallize. So you're basically freezing out crystallization. You're kinetically eliminating crystallization due to the fact that you're undergoing this spinodal decomposition and forming this glass-like network that spans the system but doesn't crystallize. And in fact, you can do some simple calculations. I won't go through them. You make one assumption about the surface tension, and you can predict the fraction of particles that actually crystallize. It's very consistent with what you do. You also can do some X-ray scattering to look at the structure of the particles, to look inside the structure of the particles, and you find that they're also not solid, but rather they're fractal-like, exactly as you would expect if they were formed originally by some kind of spinodal decomposition, spinodal sample. In fact, you can also do a simple experiment. I'm sorry for the poor contrast here, but this is a collection of amorphous material that we collect, something that's it's a supercooled fluid, so it's an amorphous material that normally wants to be crystalline, but we've maintained it amorphous by collecting this spray-dried amorphous material. The actual material is phenofibrate, which is a generic drug that's very strongly crystalline, and if we just put a drop of water on, you can see that this doesn't evaporate, or doesn't dissolve, but this completely dissolves. The water just dissolves it. And that shows that the amorphous material is much more soluble in water than the crystalline material. You can actually look at the stability of the amorphous material, and it remains stable over long periods of time. The reason, of course, is that because it's amorphous, if something turns into a crystal, it's only that one particle that crystallizes. As long as you can keep the particles separate, that is, you keep them somehow stabilized, then they'll crystallize, but they take forever to do it. They're very, very strongly delayed. So it's actually a very, very stable material. So finally, what is the one material that you are most familiar with that's always crystalline? In fact, it's on your table almost every night, and that's salt. Table salt is always crystalline. It's always crystalline until you make it small enough. If you make salt below 5 nanometers just by spray drying it, it's also amorphous. And here's some examples of the amorphous material. And just to prove that it's amorphous, we took an electron microscope and we heated it. And you can start to see that as you heat it, it starts to crystallize, and it forms the lattice of salt. So even something that is strongly crystalline as table salt can be made amorphous just by spray drying it with this type of spray dryer, with these tiny, tiny particles, by nebulizing it. So this is a very, very generic way of making both very small particles and making amorphous particles. And with that, let me stop, and I hope I've told you something that doesn't involve symmetry. It's the exact opposite of symmetry. It's how you go from crystalline to amorphous materials, but I hope it's a more general way. I think the first speaker said that 90% of physics is not perfectly exact, and this is part of that 90%. So with that, let me stop, and thank you for your attention.
Thank you, Dave, for the great review. Do you have questions? Yeah.
Is it possible to study the melting of the superheating of the melting transition in a perfect crystal, in some way suppressing surface melting and has a crystal with no defects?
Well, the only perfect crystal that I know how to do it is these colloidal crystals. If you think of a normal material, I don't know how to prevent, I don't know how to avoid the interfaces. If you can avoid the interfaces, then you should be able to study it.
Using a temperature gradient, for example, and just heating it by a focused laser beam or something like that, and looking at the way the melting takes place.
You might be able to. I mean, in fact, some of the early experiments of the colloidal systems were done by locally heating it with a laser beam. So that's a good idea. We haven't done that.
Somewhere over there.
Yeah. Hi, Dave. Beautiful talk. Many colloidal crystals are highly imperfect. What makes these particular crystals so good? And is there any parallel in atomic or molecular systems?
So the reason this is perfect is that the interaction is very soft. It's because it's repulsive, and because the repulsion is really long range, it's a very, very soft interaction. And I don't know how to make such a soft interaction in atomic or molecular crystals. I think it really has to do with the softness of the interaction.
You mentioned that one of the motivations was to be able to dissolve material which is not normally soluble in water, for example, for drug delivery. A, can you give an example where you've succeeded now? And B, when you do this, do you indeed find still the insoluble fraction of material that was crystalline remaining insoluble?
I actually showed you 4 examples of generic hydrophobic drugs, fenofibrate, clemizole, and I forget what the others are, but we've done several examples of these things. And we always work, when we're trying to do this, we work in the situation where we can keep everything amorphous. So if we go to small enough particles, we of course have to stabilize the particles, so you have to put some coating on them to keep them stable once they're formed so they don't coalesce. But then you can keep the whole system amorphous. So we haven't looked at the case where some is amorphous and some is crystalline. But when we do make it amorphous, then it is very soluble.
In the first part of the talk, when melting was almost two-dimensional, you measured the fractal dimension, you measured critical exponents. Do they agree with some standard theoretical models?
Well, I wish I knew some standard theoretical models that would predict a critical melting in 3 dimensions. So maybe you know some, I don't.
Okay, so maybe one last question.
In the melting transition, could topological defects play any role?
Could what, sorry?
Topological defects.
I don't know. That's something for a much more modern question. Maybe you can answer that. I don't know.
All right, so let's thank Dave again for the beautiful talk. And we're now moving to the physics building. Because we're late in time, I suggest that we reconvene for the review session at around 12. And I'll see you there. Thank you.